So we talk about various conditions of stationarity for a stochastic process in the second question. So White's stationary process. A stochastic process is considered White's stationary if its mean is a constant and its autocorrelation function depends only on the time interval in which we have considered the autocorrelation. So suppose we consider the ACF from time in the time interval t1 to t2, then the ACF function should only depend on t2 minus t1 or the mod of t1 minus t2. So it's a more relaxed form of stationarity, much more relaxed than strict sense stationary. So for some process, White's stationary implies that the process is strictly stationary. For example, for Gaussian or normal process and for Markov process, because for those processes, if we have the second order statistics, then we can fully define up to the nth order statistics for the process. So for such process, WSS implies strict sense stationary. So these are the conditions for White's stationary. The expectation of x of t should be a constant, and the autocorrelation taken over the time interval t1 t2, it should depend only on t1 minus t2 or t2 minus t1, the mod of them. So strict sense stationary, it is a more absolute and strict and stringent form of stationary t condition. So it essentially implies that a stochastic process is strictly stationary if the nth order statistics, they are independent of the time shifts for any value of n. So if we shift the stochastic process, the nth order statistics does not change. So if any stochastic process follows this, then it is strictly stationary. So it is the most stringent form of stationary t condition that we can have. So for some processes, White's stationary implies that it is strictly stationary, but mostly it is not. But if a process is strictly stationary, it is definitely White's stationary. So a Markov process is a general definition for a stochastic process. It's a name for a stochastic process which can be completely described up to their nth order if we only know up to the second order statistics of the process. So any good wireless channel follows Markov model. So there are only essentially two states that the process follows, a good or a bad state. And so the occurrences of the event only depends on the previous occurrences and not on other occurrences. So that is how an ideal system should be. So Poisson and Gaussian processes, they follow Markov model. As for both of them, if we know the second order statistics, we can derive up to the nth order statistics. So white noise is nothing but it's a process which models the random noise in a communication channel or any other electrical system. So the reason why white noise is very difficult to isolate or suppress is that it is uncorrelated. So if we take two samples of white noise in various different times, they are completely uncorrelated. There is no relationship between them. So it becomes all the more difficult to isolate the noise from whatever channel we consider. This is the equation form of uncorrelatedness. So expectation of WT1 minus the mean at the time t1 into, this is the autocorrelation factor. So it is 0, which means that the noise is uncorrelated at two different intervals of time. Thank you.